Hi, I'm Amy. Today we're going to talk about the common sense behind piecewise functions. You can go to my website and print out this reference page so you can follow along. The first example, f of x, is in three different pieces. One piece for the values when x is less than 2 is x squared. So you'll notice when x is equal to 2, we have an open circle here, and then the parabolic function here representing y equals x squared. And there's an arrow here at the end showing that it keeps on going. When x is equal to 2, our output value is 6, and that's why there's a point right there, 2, 6. And then the final piece is 10 minus x. And that's valid for when x is greater than 2 and when x is less than or equal to 6. So you've got an open circle here when x is 2, a filled in circle here when x is 6, and this line segment represents 10 minus x. If it had continued, it would have a y-intercept up here at 10, and of course it has a slope of -1. So that's your first piecewise function. The second example only has two pieces to it, and it splits where x is equal to 0. So you'll notice the first piece for when x is less than 0, linear function. It would have a y-intercept at -4, except for we have an open circle there because x is not equal to 0 for this portion of the function. This is only valid for x less than 0. So the rest of the function, of course, it's linear with an arrow at the end, and we're seeing a slope of -3/2. So down 3 over 2, and that continues off to the left forever and ever. The rest of the function starts at x equals 0, and it's for all the x values greater than 0, and it's represented by square root of x minus 1. So there's your first point here at 0, -1, and of course that square root function is going to continue over here to the right with an arrow representing that it goes on forever and ever. Your final example here at the bottom, f of x, is split into 4 pieces. All right, so the first piece is valid for when x is less than or equal to -2, and that f of x is equal to 1 for that domain. So 1 is a constant, and so you'll see here for -2 and all the values below, you have a constant function of 1. There's an arrow showing that it keeps going off to the left. Between -2 and 3, but not equal to those, we have x squared. So you have your parabola, basically y equals x squared, but we've got an open circle here at -2 and an open circle here at 3, 9. All right, the next one is when x is 3, the output value is 3. So this is a point again, so 3, 3, and you see the point right there. And then finally, for all the values of x that are greater than 3, you've got this linear function. And so we have an open circle because it's not equal to 3, it's just for x greater than 3. And it is a linear function with a slope of -3. If it continued on, it would have a y-intercept at 11, so you can use that to help you graph it if you need to. You can take your straight edge and figure out where 11 is, and you can use your slope of -3 to create that line if this was a problem you had to work on your own. So on the back side of that page, we have 4 examples that you're going to work yourself. So you can pause the video now and work through these yourself, and then come back to the video and see how you did. So I'll give you a second to pause. So let's see how you did. For the first function, f of x, we're looking at -3 as the output value for all the values of x that are less than -1. -3, of course, is a constant function, and it says less than, not less than or equal to. So I know I'm going to have an open circle there. So I'm going to go to, let's see, -1 would be here. And I want to go down to 1, 2, 3, -3. I have an open circle there. And then I want my linear function to continue to the left. And I can just put an arrow there to represent that it keeps on going. Next, I have a point. So at -1, I have an output value of 0. And so I'm going to make that nice and dark so I can see that there. And then finally, for x values greater than -1, we've got this -x squared plus 4. It's an upside down parabola. So I know that this parabola would have a y-intercept at 4, and I also know that at -1, I'd have 4 minus 1, so I'm going to be here at +3, so open circle here. And then, of course, over 2 and down 1, 2, 3, 4, and over 3 and down 4, 5, 6, 7, 8, 9, and so on. So I've got this parabolic function, and I'll put an arrow at the end. There you go. So for example number 2, f of x is equal to this rational function for all values of x that are not equal to 2. Hopefully you see that this makes sense, because if you plug in x equals 2, especially in the denominator, you're going to get 0. You'll get 0 over 0, and that tells us nothing. That tells us that f of x cannot be defined by this rational function at x equals 2. But if I reduce away the x minus 2's, I'm left with x plus 3, and that's the shape that this graph is going to take. It's going to take the shape of a linear function with a y-intercept at 3 and a slope of 1. What I can do is graph for all values of x except for x equals 2, I can graph this linear function. I'll just leave a hole in the line when x is equal to 2. So y-intercept at 3, and it has a slope of 1. Okay, and so when x is equal to 2, there will be a hole in the function. So I can go ahead and graph this. And I'm going to go ahead and put a line here and a line here. So that's the first portion of the function for all values of x not equal to 2. Of course, 2 is right here. When x is 2, we have the output value of -1. So that's just a point at 2, -1. So we have a linear function with a hole in it, and then of course at 2 our value is defined down here at -1. For problem number 3, okay, really similar situation. We have a rational function that's defined for all values of x except for x equals 1. If I was to reduce away the x minus 1's, I'd have this linear function y equals x plus 5. So I know that function would have a y-intercept at 5 and has a slope, again, of +1, but of course would have a hole here when x is equal to 1. So again, I can kind of graph in the linear function here, and it goes off in either direction. Put arrowheads to imply it goes on forever and ever. And of course, we've got the hole there because this function is not defined right here with this portion when x is equal to 1. The rest of the function says, okay, when x is 1, the output value is 6. And coincidentally, 1, 6 is exactly where that hole is. So this value of 6, in effect, fills the hole. The final problem, again, very similar. We've got a rational function that is not defined when x is equal to -1. So if I reduce away the x plus 1's, I've got a linear function of y equals x plus 4. So again, y-intercept at 4 and a slope of 1. At x equals -1, I'm going to leave a hole there. And I can go ahead and graph in the rest of the function. So line that direction, goes on forever and ever. That's why I put the arrowheads there. And then it says k. F of x is equal to some constant k when x is equal to -1. Well, k could be any number in the world. K could be -5, k could be 107, k could be pi, k could be anything. So now the question here says, what value does k have to be in order for f of x to be continuous? Believe it or not, this is a pretty common question that you'll see in calculus. And if you hadn't worked with piecewise functions, might seem kind of confusing. But really, hopefully this seems kind of logical to you. What value does k have to be in order to fill in that hole right there? At -1, we need our output value to be 1, 2, 3. So hopefully you realize that k needs to be 3 in order to fill that hole. Thanks for joining me.